Well, hello everybody and welcome. My name is Bill Cope, and I'm going to speak to a project that we're doing as part of this Jump Archers scheme, which we call MedLang. I'm going to swap over now to a PowerPoint presentation where we can give you a quick overview of the work that we've been doing. So I hope everybody can see that image okay. Um, so this is an initiative that we have called MedLang, and you can see an image there in the middle of this kind of essentially it's a modeling tool. And I want to introduce also the other people who are part of the project: Mary Calancis, who's online, Dwayne Searsmith, who is the developer in this project, who's online, Chengsheng Tsai, who's online, who's been working with us around AI data mining issues for some time now. Richard Tapping unfortunately can't be online because he's got another meeting today. He's working with us at the University of Illinois College of Medicine in Peoria. And you know, our reference point really is some of the uncertainties, confusions that involved COVID-19. That's just one example of the kind of thing we might be tackling. So COVID-19 seems to be a single thing that hits populations. Well, no, it's the way in which it operates is extremely variable in mysterious ways, to be quite frank, or ways which are becoming only clear with time. So one of the things is we can think about COVID-19 or any such medical event as a population event, but in fact, in every case is a single case. And that when there's even small numbers of cases where things align, that's of extreme relevance. So these are some quotes early on where the CDC and the WHO were dealing with data, which was kind of frustrating in a whole lot of ways. The bottom left-hand corner is a quote from Ilu Herta at the symposium back on April 6th, where he said, look, you know, we've got all this data, but it's not really adequately labeled. So it's it's this labeling issue that we're dealing with. Now, this here is a screenshot. This is a web-based application. So this screenshot is actually of a web application. And it's a screenshot where I'm going to kind of explain how this thing works. And then in the next slides, talk about, well, look, what does it mean? Where can we take this? So this on the left-hand side, and I hope you can see my cursor. Maybe you can, maybe you can't. The left-hand side is a text created by a U of I medical student in an autoimmunity unit. And this particular student's doing a clinical case study of a hypothetical person with diabetes. So what she's done is she's written some text, she's put in some images and diagrams, she's labeled them. So this becomes a kind of a case analysis, and it scrolls on beyond what you can see there on the screen. Now, what she didn't do, which we're now doing to her text in this screenshot, because it's this new app that we've got working, is over here, what you can do is you can build a kind of a concept map of what's going on. And what you do is you take a stretch of text here, you highlight it, and then you search for that concept across multiple medical ontologies. It might be SNOMED, it might be ICD, and in fact, we've loaded many medical ontologies into here. So what it's about formalizing what's in the narrative on the left against a data model on the right. And what we're then doing for her, and she would have done if she had the tool, is we are busily building a kind of a logic model of what's going on. So the conceptual architecture is that on the left, we have data, which in this case is about a diabetes case, and we've got empirical evidence. And on the right, what we've got is metadata, which is pulled out of these schemas, and we're building a logic model. And then on the right here are some generalizations, which in fact Cheng made and added to these slides. I'll get him to speak to them in a second, is that we've got data integration. Effectively, we're able to use more data. We need less data to explain predictions. And I'm going to actually turn over to Cheng in a moment to go into those points. But before I do, let me say what the ontologies on the right side can involve. So firstly, there's a whole lot of medical ontologies where we can use multiple ontologies, and we've loaded all of these listed in the top part of the page. They're all loaded in. But in fact, what we could also load in is contextual ontologies, place. I mean, we know that various medical conditions are, might be place dependent. Time and event, demographic profile, occupational classification, but also, out in the world, there are just so many more of these things. For example, objects in the form of identifiable products. So what we have in the world of, what you might want to call the semantic web, the Internet of Things, there are a whole lot of cliches to describe this world, is we have stuff where ontologies precisely specify what things mean and what their relations are in very, very granular ways. These can be leveraged. So what we want to do with this is argue to move from a population paradigm to a precision paradigm. By a precision paradigm means, look, what is unique about small numbers of cases and single cases as opposed to big populations and correlations? That's at least as important. Whereas conditions are tracked on the basis of pattern repetition, no two contexts and pathways are the same. COVID's a good example of that. Some people die for some reasons and some people don't, and the reasons are not always clear, and maybe we can track down some of those reasons in ways which are useful. What we do in a population paradigm is we cluster. What we do in a precision paradigm is about granular causal relationships. We've got big data, but on the right we've got little granular data, tiny things where we can look at these tiny relationships. But in the population paradigm, explanation is a big inference and a big jump a lot of the time, whereas with little data, we're hoping we can get closer to particular causes of things and then perhaps generalize out from that. So what it's about, this project is about integrating precision data with population data. So here are some examples of what we might do. You've already seen this. This is a student, right? So they've got their case and they're doing clinical on the left, and they're doing clinical reasoning, and they're kind of thinking aloud. This is kind of explicitly thinking through their reasoning. And if you like, it's a second layer of reasoning, which really is a way to refine the thinking. We've got the narrative of a single case on the left, and we've got clinical reasoning there on the right. What we might do is we might do the same, and this is actually the same image repeated. I mean, what we do in medical science is journal articles based on populations. But again, why not be able to do these very, very thorough analyses, hospital-based analyses, research-based analyses of single cases in order to look for this causal stuff? The other thing we've got in mind is the possibility of perhaps a smart medical record. So what we might be able to do is in some way overlay this via a shadow box or via various forms of capture of what's happening inside a record. We don't want to touch the record or particularly influence the record itself, but we might be able to build a layer over that, a kind of a map of what's going on, but also a suggestion system for decision support around processes, suggestion system, a smart suggestion system, leveraging ontologies to do that, but also to support accurate coding. We know that one of the big problems about medical communication and the whole insurance system and everything is accurate coding is an issue. And the fourth case is we might be able to take medical data sets and annotate them in a way which is much more granular than possible at the moment. So this is where we're going in terms of some challenges and potentials. And what I might in fact do is, Cheng, would you, this is a slide which I did a first draft of and you wrote it. I wonder if you'd mind speaking to this slide, Cheng.
Yes, sure. So, so basically, what Bill has explained is, what we have in mind and what we could potentially do. And you can see many concrete examples where such an annotation tool can significantly enrich the representation of a data instance and can bring humans in the loop to kind of collaborate with machines. So here are some concrete challenges and potentials and that we can really pursue by leveraging the tool. So in one line, we can basically enable the current machine learning applications to be more explainable. So towards explainable precision medicine. And this can be achieved by two ways. One is to augment um, human intelligence. And essentially, we have AI systems to be assistants to help us make decisions, to allow us to see patterns that we would otherwise not be able to see or see clearly. Here we can clearly leverage the interpretable patterns in the evidence and to use them directly as insights and suggest a new hypothesis. Because previously, if you just look at the patterns in medical records, you might see some numerical associations and some of the variables maybe correlated and you see clusters. But now, because of that mapping to the ontology, you can now interpret those patterns more directly, and it might be more meaningful and can potentially suggest interesting new hypotheses to look into. And another way to achieve augmented intelligence is to deepen the relations within and across ontologies to further extend our knowledge base. And this is where computers can help humans to further review relations among these ontologies that are annotated on different cases. When we link them, when we do analysis of them together with data, we can further enrich the connections across different cases. The other line to help us achieve this goal is autonomous intelligence. This is where we can potentially use machines to, again, to replace us and in some simple tasks. And in many, there are many such applications. For example, machine learning has been used to automatically read CT scans and try to interpret the images. And so in all these cases, machine learning programs will be used to predict certain labels that we are interested in for data instance. But they currently are relying on mostly sophisticated statistical pattern recognition to make such predictions. And so as a result, they cannot easily explain why they have predicted the result in a certain way. And without explanation, it's going to be very hard to make use of the prediction results. Nobody can trust such prediction results, even though they are actually correct. We cannot easily adopt such results without explanation. And that's where I think these enriched semantic annotations could help a lot, because machine learning programs could basically pick up patterns from the ontology as a way to explain why these instances have been classified in a certain way. The other dimension, of course, is to make this kind of annotation scalable so that it still involves a lot of manual effort. So the question is, how can we kind of use machines to help us make such annotations more efficiently and to minimize our effort? So we could envision AI-aided annotation, use human-generated data to train a machine learning algorithm to do the same, or support humans by making smart suggestions. And machines could pick up patterns in the human-generated data and then suggest, oh, for this patient case, do you want to use this part of this ontology or these relations? So this would help us improve the efficiency of annotation. And the other two directions are related to ontology, directly ontology alignments. And this can reveal semantic overlap or differences. Again, machine learning algorithms could be used here. And in turn, these better aligned ontology, again, further enriches the annotation, which can always help improve explanation ability of a machine learning algorithm. We can also think about ontology extensions. And so we have validated user extensions and qualifications as extensible annotation schema. So this would grow the ontology and then improve the efficiency of annotation so we can scale up MedLang. And we have been also thinking about other applications. Of course, one is still in the medical domain, and to use the data annotated and the tool itself as medical training tool. And we can, for example, generate the simulation cases of patients based on real patients' data in a more realistic way. And these synthetic patients can then be used for education purposes. And the tool is not restricted to the medical domain because annotation of semantic information in data science is generally needed in order to make machine learning algorithms more explainable and also to enable them to kind of be supervised in a more intelligent way by humans. Therefore, it would alleviate their need for a lot of data. So clearly, we see a lot of opportunities to go beyond the medical domain to leverage MedLang. We might as well call it some XLang and some other domain applications and a different acronym. But the idea is the same. The idea can certainly be generalized to enable a lot of applications.
Great.
Thanks, Bill.
Thanks very much, Cheng. So that's really the end of our presentation. I just wonder whether other people in the group, Mary, Dwayne, Duncan, would like to say anything as well. We're looking ahead now to form, R&D collaborations. Anybody involved in medical education, teaching and learning, the whole medical informatics area, but generally AI applications in medicine. We're looking to NIH, NSF. We've had an NSF grant previously in this area, so we're looking to other funding opportunities. So if any of the others would like to jump in, or if there are any questions in the group, you can either jump in with voice, or you can put the question in the chat box. Okay. Well, look, I thank you very much for joining us in this presentation. Just to close off now, to end up. I mean, one of the things that we do in the whole AI area is rely an awful lot on the algorithms, the statistical work. But increasingly, I think people are coming to recognize that the data models themselves, the semantics that underlie these is incredibly important as well. So the challenge is, how can we build a dynamic relationship between the data models and the algorithmic work? So if there are no other questions, folks, and no other comments, I might say stop the recording and say thank you all very much for being with us.